Like to introduce tonight's program and speakers who will present some of their research pertaining to the very timely topic of tracking extreme weather and hurricanes. Dr. Nan Walker is the director of the EarthScan Lab, LSU's on-campus satellite data receiving facility and image processing lab that captures and processes and archives real-time data and animations of the current weather, hurricanes, and ocean currents from a variety of NOAA, NASA satellites. Dr. Walker uses satellite remote sensing to study how Gulf of Mexico currents and eddies impact tropical cyclone intensity. She is the James P. Morgan Distinguished Professor of Coastal Studies in the Department of Oceanography and Coastal Sciences in the LSU College of Coast and Environment. Dr. Jill Trepanier studies extreme climatic and weather phenomenon, specifically tropical cyclones. She uses quantitative methods such as statistics to analyze these events. She is an associate professor in the Department of Geography and Anthropology in the LSU College of Humanities and Social Sciences. Her current research interests include understanding extreme weather events, tropical climatology, climate change, geographic information systems, risk assessment, and statistical methods. Dr. Barry Keim is the Richard J. Russell Professor in the Department of Geography and Anthropology in the LSU College of Humanities and Social Sciences and serves as the Louisiana State Climatologist. His research focuses on climatic extremes with particular emphasis on heavy rainfall, hurricanes, storm surge, and the interpretation of climate data. As state climatologist, Dr. Keim conducts climatic research on the state of Louisiana and the broader region and serves the community by providing climatic data to those in need, including researchers, government agencies, police departments, and the media. He also oversees a group at LSU that manages the world's largest and most comprehensive database on global storm surges. After their presentations, we'll have a moderated question and answer session. To participate, please use the Q&A button to enter your questions. We'll be monitoring that section and relaying them to our panelists. And now it is my pleasure to introduce Dr. Nan Walker. Nan, if you can go ahead and turn on your camera and mic, and we'll be ready to go.
Good evening, everyone. My presentation tonight will focus on how the ocean impacts hurricane intensity changes based on my research at the LSU EarthScan Lab. I would like to acknowledge my colleague, Alaric Haig, the lab system manager, for providing an animation of Gulf temperatures from the new GOES satellite, which I will show at the end of my presentation. For over 20 years, scientists have realized that forecasts of intensity could be improved significantly by incorporating accurate ocean and atmospheric data from satellites, and specifically into their hurricane models. Hopefully, with the recent launch of the new and improved GOES sensor, these advancements will soon be realized. Although LoRa's track was forecast with unbelievable accuracy, the intensity was underpredicted by 50 miles an hour. The two most important satellite measurements of the ocean for intensity research are sea surface temperature, or SST, and sea surface height, or SSH. SST is defined as the temperature of the upper 1 meter, whereas SSH reveals information about the vertical structure of the temperature at depth in the ocean. Together, they are used to compute the heat available to the hurricane, or the ocean heat content, OHC. OHC is based on the depth of the 26°C temperature, which is known as the minimum threshold for hurricane formation and maintenance. In the Gulf, two main types of current features are observed. The first type of feature includes the loop current and warm core eddies, which have high values of SST, SSH, and OHC. These features provide an unlimited source of energy to the hurricane. The second type of feature is the cold core eddy, which has lower values of all three variables, and it provides little or no fuel for intensification. The color images at the right show SST based on GOES East satellite data in August of 2005, before and after Hurricane Katrina's passage. The same color scale is used for both images, so the changes that you see in color depict impacts of Katrina's wind and wave field on surface temperature patterns. The top panel shows the Gulf sea surface temperature 5 days before Katrina hit the coast, and the bottom panel shows SST 3 days after its landfall. The highest SST is shown with dark orange, and lowest SST is dark blue. You'll see that Gulf temperatures were highest before Katrina crossed the Gulf, with mean temperatures near 32 degrees Celsius, or 90 degrees Fahrenheit. Notice that across the entire Gulf, SSTs were very high. In summer, Gulf temperatures become very warm due to strong solar heating and lack of wind mixing. Lowest temperatures are seen in the post-Katrina image, and they were near 24 degrees Celsius, or 75 degrees Fahrenheit. Next, I would like to show you the loop current. In the top image, the margin of the loop current is marked with white arrows. The warm waters flowing from the Caribbean Sea between Mexico and Cuba become the loop current upon entering the Gulf of Mexico. Upon exiting the Gulf, the loop current waters are called the Florida current. The many closely spaced solid black lines within the white arrows within the loop current indicate high values of sea surface height. Although the loop current is not clearly visible in sea surface temperature data in summer, it is clearly visible in sea surface height data as a high in sea level. Dashed lines indicate low sea surface height areas in cold eddies, and they are prevalent around the loop current. Sea surface height lines are shown in both the pre- and the post-Katrina images, but the details are more easily seen in the post-Katrina image due to its higher zoom factor. The track of Hurricane Katrina is shown with dark black lines in both images. Also shown are the wind speeds every 6 hours along its track in miles per hour. In the top image, if you concentrate on Katrina's track, you will see that it moved into the Gulf from southern Florida, and when it encountered the loop current, it began to intensify very rapidly. It reached Category 5 strength with 173 mile-per-hour winds after only 30 hours of the loop current. However, upon leaving the margin of the loop current, the hurricane intensity decreased rapidly from Cat 5 to Cat 4. The post-Katrina image reveals a large area of extreme sea surface cooling within a cold core eddy north of the loop current along Katrina's track. Temperatures fell below 26 degrees Celsius. If we had had an image sooner after hurricane passage, the SST was likely even colder. Thus, the cold water entrained to the surface by Katrina's giant waves rapidly cut off the fuel to Katrina, and as a result, its intensity decreased before landfall. The previous year, a major hurricane called Hurricane Ivan experienced 2 cold core eddies along its track. And with better satellite data, we were able to observe that the cold features were an immediate response to the hurricane winds and waves. Also noticed in the post-Katrina image that the waters are much colder to the right of the track after Katrina's passage. This is because the winds are stronger on the right side of the track, causing more entrainment of cold water to the surface. The stronger winds also cause more evaporation, which cools the surface ocean. And the ocean's heat is transferred to the atmosphere, fueling the hurricane. Although I've only talked about the ocean's impact on hurricane intensity, events in the atmosphere also play an important role in hurricane intensity changes. Thus, it's critical to monitor both ocean and atmosphere to accurately predict intensity changes. Next, I'd like to show you an animation of the Gulf sea surface temperatures starting in December 1st, 2019, ending August 31st, 2020. My objective is to show you how rapidly the currents can change in the Gulf and to show you the loop current and eddies that separate from it. So you will see the loop current is a yellowy orange color, and right now in February, you can see a warm core eddy has separated from the loop current. Now the loop current is being entrained by that warm core eddy, and the one warm core eddy appears to have split into two. Now as summer progresses, you see the temperatures in the Gulf are getting much warmer. Tropical cyclones moving through are seen as purple patterns. Now you can see the loop current is actually a little colder than the rest of the Gulf, because in the summer, the Gulf becomes extremely warm. And the loop current, because it has a lot of mixing because of the high velocity of the currents, it remains a little cooler because the cold water is mixed upwards. So I know that went by very quickly, but if we backed up a couple days, you would see that the Gulf temperatures were very isothermal. In other words, they were very similar across most of the Gulf. They were about 31 degrees Celsius or higher. Plenty of fuel to intensify Laura. Laura was seen to move very rapidly over the loop current, which was in the eastern part of the Gulf, and then it moved over a cold core cyclone, which you can't see in this animation, but well, you can actually, after the storm moves through, you do see a little cooling in the ocean, but it doesn't look extreme. Another source of satellite sea surface temperature information we have comes from microwave sensors, and those do not have clouds in them. The resolution of that sensor is much reduced. It's only 25 kilometers compared to 2 kilometers. But because there's no cloud contamination, it's also very useful for hurricane intensity studies. All right, so it's likely, just looking at the ocean temperatures and the features in the Gulf right before Laura, that both the ocean and the atmosphere were responsible for its rapid intensification. Thank you.
Great. Thank you, Dr. Walker. Well, now it's my pleasure to introduce Dr. Jill Trepanier from the College of Humanities and Social Sciences, and she's going to be talking about her work on hurricane intensities.
Hello, everyone. I'd like to draw your attention right away to the left-hand side of the screen. One of the areas of research I like to focus on is understanding how often an extreme hurricane will happen and where it might happen. The top graphic is looking at what we call a 30-year return level. It's how extreme a hurricane can be in a 30-year period of time. Each one of those hexagons represents a local return level, and that scale represents the meters per second scale, with the highest being 167 miles per hour, which is well into a Category 5 hurricane. If you look at our historic return level, what I mean by historic is if I use all of the data that's available to me in the North Atlantic over the known record from 1850 to today, this is what that expected return level looks like. My next question relates that intensity to sea surface temperature, much like Dr. Walker was just talking about. If I want to locally understand how sea surface temperature impacts the wind speeds in each hurricane, I can isolate that by looking at it geographically. With these hexagons, I can look at the average sea surface temperature over time and increase it by, say, 3 degrees Celsius. That allows us to get into the world of anomalous sea surface temperature we seem to look at a lot today. Then I can adjust the wind speeds associated with this localized sea surface temperature sensitivity, and then rerun my model and get what I call a future expected return level. You can see that well throughout the main development region into the Caribbean, kind of have to tilt your head this way a little bit, you'll see that Florida, the island of Jamaica, Cuba, the Dominican Republic, the Yucatan Peninsula are all well under a Category 5 wind speed in a 30-year return period. This means that we can expect those more extreme storms much more often, and a lot of that is related to that increase in sea surface temperature. If everything else is moving in the direction for making one of these storms work, then we should see more extreme storms. The bottom graphic is just showing to you the overall change or the difference between those two graphics. And you'll see that in some places it's up to 8 meters per second. But what's important to notice here is that the geography is not the same everywhere. As a geographer, it's important that I look at this spatial variation in return level risk so that I can better understand how to talk to the people in those areas and tell them the kind of risk that they can prepare for. The superimposed tracks there with the red coloring being a category 5 are the storms from the 2017 season. Now I'll bring your attention to the right-hand side of the screen on the top. My student Kathleen Benedetto and I have been working on some understanding of rapid intensification and systems. That picture of Laura you see below is a storm picture right before it made landfall. And that graphic above is to showcase to you where we tend to see rapid intensification events reach their lifetime maximum intensity. What that means is every storm, while it progresses through its lifespan, reaches a maximum intensity at some point. If a storm is rapidly intensifying and ultimately makes its way into the Gulf of Mexico, we're seeing more storms reach that LMI, that highest peak in their life cycle, right before they make landfall. And that is, of course, very devastating for anybody who lives in those areas because that change happens very quickly, as we saw with Laura. Finally, the research that I wanted to bring to your attention in that small bottom picture in the right is the education outreach I've been working on as well. I paired with Louisiana Sea Grant as well as the Coastal Roots Program and Pam Blanchard at LSU with some sociologists, Mark Schaefer and his student James Jordan. My student Clay Tucker and I, who's now graduated, Dr. Tucker, we've been working on understanding how we can better prepare teachers in the environmental science realm in K through 12, as well as their students to understand climate change, climate science, and doing it through dendrochronology. This all relates to hurricanes because some of the work that we did allowed us to understand whether we could see hurricane signatures in trees. If a storm was severe enough, both in storm surge or in wind speed, we might be able to tell that in a tree core. By going into the public and teaching the students as well as the teachers how to actually use this material, it allows us to instill an understanding of climate science and climate change to a younger population that will ultimately, hopefully, grow up to continue to think about the environment and how they might better understand it and better protect it. So these are the 3 areas I wanted to focus on today. And I do a lot of research in other areas as well. And if you have any questions, I'm more than happy to talk to you about them.
Thank you, Dr. Trepanier. And now it's my pleasure to introduce Dr. Barry Keim, who will be talking about his work on some of the hurricane signatures that are that we witnessed so clearly just last week. So Barry.
Thank you. Yeah, so what I want to talk about is hurricane signatures, and what I'm referring to here is this triple threat that hurricanes pose in the form of surge, rain, and high winds. And of course, all hurricanes have some semblance of all 3 of these, but for one reason or another, in any given storm, one of these sometimes becomes more impactful or across a given area. For example, I mean, surge kills more people than the other 2 signatures by far. In fact, about 90% of the people who have died in hurricanes over the last, say, 150 years or so, perished because of surge, drowning in large surge events. And because of this, we built a surge database here at LSU. It's called SurgeDat, which stands for Surge Data or Surge Data Set. And from that data set, I'm able to put together this top 10 list you see in the upper left-hand corner with the ranking of the top 10 surges. You can see Katrina and Camille come in as 1 and 2 with a 28 and roughly a 25-foot surge, respectively. They both occurred at Pass Christian, Mississippi, and that is no accident, given the setting there between the delta of the Mississippi River and the configuration of the Mississippi coast, and the water gets sort of channeled into that region and then rechanneled into Bay St. Louis. Then you can see, Texas and Florida is well represented in some of the ensuing surge events, and Louisiana has 2 in the top 10 as well, with Rita with a 17.8-foot surge, as well as the hurricane of 1915 in New Orleans that also produced a 17-foot surge across southeastern Louisiana. And the graphics or the images I have underneath are pictures of the surge in Hurricane Katrina. The upper picture is actually Chalmette, Louisiana, in St. Bernard Parish. And there we probably had 10 to 15 feet of standing water on the ground. All you see are the rooftops of the houses poking out of the water. I actually grew up about 2 blocks off the left edge of that particular image. The house I did grow up in is shown in the bottom left-hand image. One of our neighbors who rode the storm out actually snapped that picture. I grew up in that 2-story white brick house with the dormers. Of course, our neighbor's house across the street, you're seeing the roof poking out of the water. And just to the right of that image is the infamous barge from the industrial canal that got sucked into the lower 9th Ward. In some of our research at LSU, what we found is that the strength of the storm at landfall, while obviously that's going to be somewhat of a decent indicator of how much surge you're going to get, but what we actually discovered was that the strength of the storm 18 hours before landfall has a stronger correlation between the strength of the storm and what was taking place actually at the coastline. Katrina is a great example. Katrina was a Category 5 hurricane with 173 mile per hour winds 18 hours before it hit land. It weakened to a Category 3, but it was still packing that Category 5 surge when it slammed into Louisiana and Mississippi, producing a 28-foot surge at Pass Christian. Laura, on the other hand, was a stronger storm at landfall, but was weaker 18 hours before landfall. And the surge wasn't nearly what we saw in Katrina. In fact, it was probably about a third of what we saw in Katrina, even though it was a weaker storm, at that point at landfall. Then we have storms that produce heavy rain, and that's their real signature. Harvey is a great example. And storms that produce lots of rain are generally the ones that move very slow. So in essence, they hang out over a region for an extended period of time. They don't move along, and they just keep dropping rain in the same locations over and over again. And Harvey did a series of loops along the coastline, and it just kept raining and raining and raining and raining. Never went away. And in that upper graphic that you see in the middle there, all those areas in purple, I mean, we're talking about 30, 40, and 50 inches of rain. And we even had 2 locations just south and east of Beaumont, Texas, that had over 60 inches of rain over 5 days. That's our annual total for the state of Louisiana. Okay, so that happened in 5 days at these 2 locations. And through processing of some of those data, we put together what's called a DAD table for depth, area, duration. And for these two area sizes, at 35,000 square miles, we had 22.6 inches of rainfall in Hurricane Harvey. That's an area about the size of South Carolina. So think about dropping 22.6 inches of rain across the entire state of South Carolina and what would play out. And over 2,000 square miles, we had 42.2 inches. That's about the size of the state of Delaware. And again, think about putting 42 inches over Delaware in 5 days, and what would happen? Well, that's what transpired across Beaumont and Houston in Hurricane Harvey. It is totally mind-boggling. And in terms of the total volume of water, this is probably going to be the greatest storm, certainly in the history of the United States and probably beyond. And then those last 3 panels on the bottom, I just kind of highlight the August 2016 flood that we had here in Louisiana. In the graphic with the rainfall and the colors, the magenta, everything inside of that is 10 inches or more. Everything inside of the sort of the mauve or purple is 15 inches or more, and then the white is 20 inches or more. And we had a site at Watson that recorded over 31 inches of rain in 2 days. And then the graphic next to that with the colors, all those deep red colors, all those areas, this is in the Amite Basin, all had greater than a 1,000-year storm event take place at those locations in terms of the 2-day rainfall totals. And then there, of course, you can see me standing in front of the iconic Louis Café in knee-deep water out in the middle of the street. So, and then we have storms that produce high winds. And storms that produce high winds obviously have to be a very intense hurricane to begin with, but also the forward translation of those storms, that translation speed gets added onto those winds, making things even worse. And that happens on the right front quadrant. I think Nan had mentioned that earlier in her talk. And of course, Lake Charles fell in that right front quadrant of the storm. And I did a reconnaissance there on Sunday, and what I saw was mind-blowing, way worse than I ever dreamed it was going to be over there. And these are some of the pictures that I took. The first one is of St. Paul's Lutheran Church, right off of I-210. The whole back of the building is blown out. The side wall is taken out, and the place was just an absolute mess. To the right of that is the Capital One building with about a third of the windows blown out. That's on the south-facing side, which would have been taking on the highest winds, but there's a significant number of windows blown out even on the backside of the building. And then just driving through the neighborhoods, I mean, you couldn't drive a series of blocks in a row without having something for the highlight reel, like you see here with a tree over a car and a tree blocking the street, or a utility pole or power lines in the middle of the street. It was just an absolute mess. And then underneath that, you can see, a house blown down, and then the Lake Charles radar tower actually destroyed. So again, different hurricanes have different signatures. Surge is the worst of these things, but Laura was a significant wind event, and I can assure you that it was a transformational event for the city of Lake Charles. So I'll go ahead and stop there.
Thanks, Barry. So now we'll have all of our, go ahead and kill that slide, Holly, and we will go ahead and start our question and answer period. If you have a question, please enter it in the Q&A section, and we will be sure to get to it. I did want to start off first acknowledging that last week we had quite a hurricane event when we had a non-hurricane event in Hurricane Marco. And I wanted to also just thank you for taking the time to reschedule so that we could have this conversation. I think the thing that's most interesting for me is what are the things that surprised you about the events of the last week? What are the things with regard to the hurricane, the hurricanes that either caught you off guard or was something you weren't really expecting? Dr. Walker, if you'd want to start.
Well, I think the rapid intensification was certainly a shock. And I don't have a definitive answer for what caused that, but obviously the ocean probably had a component, and I think the atmosphere had another component. The two together usually caused the most intense hurricanes that we experience. Same thing happened with Hurricane Katrina. So Hurricane Katrina grew very rapidly over the loop current, but at the same time, the atmospheric conditions had to be very conducive for Katrina. So I think we're kind of looking at the same thing for Laura, that both the ocean and the atmosphere were favorable for intensification. And obviously the models aren't taking that into account yet. Also, I think it was a surprise that the storm surge was a little lower than was predicted. I think Barry alluded to why, because Katrina's highest wind speeds were in the deep Gulf, and then it decreased in intensity, but the highest wind speeds caused the surge to be very, very large, whereas Laura just kept building as it approached the coast, which is very unusual. But obviously there was no cold eddy there to stop Laura's intensification either. So those are the things that come to mind right away. I haven't really studied the event in any great detail, so I look forward to that.
Barry, any thoughts on what happened to Marco?
Yeah, well, obviously, I mean, there was a lot of discussion about having two storms in the Gulf at the same time, although I don't think we ever officially had two named storms. We had just a remnant of Marco in the Gulf when Laura finally entered. But, we hadn't had two storms simultaneously in the Gulf since 1933, where we had a storm that made landfall at Cedar Key. It was a hurricane, while a tropical storm was making landfall at Brownsville. So it has happened historically. But we didn't quite get there in this particular case. But I would say the most surprising thing with this storm was the wind damage in Lake Charles. Just is mind-blowing to me. Like I said, I went there with a pretty open mind, was expecting to see some damage. But this is truly a transformational event for that area. And it is shocking how roughed up that city was. I can't even emphasize it enough. The place, even though there was no surge there, it looked very much like New Orleans after Katrina, after a major flood event tore the city apart. And it is an absolute mess. And my heart goes out to the folks that are coping with that in that particular region. But it's shocking.
And Dr. Trepanier.
I don't really have much else to add. I think they both nailed it right on the head. I would just echo both of their sentiments: intensification on one side and the sort of breaking apart of Marco on the other. And I will agree, I don't think we ever had two Gulf hurricanes at one time this week.
Okay. Well, we do have a question specifically, since Barry, you brought this up about kind of the damage that happened in Cameron Parish and in Lake Charles. What was the broadest impact on the parish itself? Would a barrier plane create significant mitigation? This is someone who knows what they're talking about. So I guess they really want a good answer from you. And is there a way that some physical barriers could be used, I think, to kind of lower the impact on wind velocities?
Wow. Yeah. Well, there's not much you can do with the wind velocities. I mean, there's all sorts of technology out there that, I mean, trying to pump cooler water from the surface of the Gulf, up to the surface. And I mean, these things would be very difficult to pull off and probably very damaging to ecosystems. And I don't really see us ever being in a position to do some of these things. But in terms of Cameron Parish, what's kind of interesting there is, I mean, we had Holly Beach in the town of Cameron, and these were interesting towns, certainly prior to Hurricane Rita in 2005. And Rita just annihilated this area and took a lot of these, fishing camps and things out that were used quite frequently by, folks in southwestern Louisiana. And my guess is, some of those folks probably rebuilt, but then Ike came by in 2008, 2 years later, also put about a 11 or 12-foot surge across this area and annihilated it again. And very few people have come back. I mean, I rode that portion of the coast, I believe it was back in January, and I was shocked at how few people are even left in Cameron Parish. So in this particular event, I'm guessing it's going to be tough to even get much data because there aren't many structures to get high water marks inside of down in Cameron. I mean, obviously there are a few, but it's not what it was prior to Rita back in 2005. And of course, there were forecasts for 15 to 20 feet of storm surge in that area with this storm. That's something that we need to figure out exactly what went awry with the surge forecasting. And I mean, it seems like the early indications are between, say, 9 and 12 feet. We're probably going to find some isolated areas where it did spike a little higher, but only time will tell. We're still gathering data on all that.
Another question has come in talking about how there's a lot of news out there that talks about how the intensification of hurricanes has happened over as the climate has warmed. What is the data that's out there to support that premise? Is that something that, I mean, other than kind of some of the statistical models that you've seen prior, what is the data that's out there now that's going to keep those trends moving in that direction?
Jill, you want to take this one? Or, I mean, I'm happy.
Yeah, sure, absolutely. I think that first, we usually look at the intensity of these events over the long period of record. So we've got about 160 or so years of data for the North Atlantic. And when we think about climate change and how it impacts intensity, you have to consider how much those data have changed over time. And in the most satellite era, the data are arguably far better. I think when we look at intensification, if we isolate the events that have become the most extreme, we look at it over time, we see that storms that are reaching a higher level than they used to. So whether or not you consider it related to sort of natural climate change or anthropogenic climate change, there is some notion that, and the data support, that the more extreme events are becoming more extreme than they were capable of before. I think that as we move forward into these seasons and we see some of these really impressive events, it helps to support the idea that a planet with more energy on it requires more energy transfer. And that's what hurricanes are. People need to understand that a tropical cyclone's purpose on our planet is to move energy from the equator to the poles. And if there's more energy that exists, be it in the atmosphere or the oceans, that energy must move somehow. And so if it's in the number of events or the intensification of the events, one way or another, something has to change. So I think some of the intensity of these events that we're seeing is related to that increase in warming around the planet.
And just to follow up on that, the modeling community is basically saying that as we go into climate change and into the future, we're likely to see either the same number of storms or maybe even less storms, fewer. But the ones that we get could potentially be more destructive. And well, a lot of hurricane researchers, I mean, there are researchers that won't even sit in the same room with each other over this whole climate change debate. So it's a very thorny one, and I'm not convinced that we're seeing a significant signature, only because our data. I mean, obviously we're seeing powerful storms recently, but we just have so much more data now than we ever had in the past, and it's hard to compare data that we have today, the satellite era data, with say the beginning of the 20th century, when we were relying on land observations and ship observations, when we had no planes really to investigate the storms offshore. So our data sets are way better now than they used to be.
So speaking of data sets, I know, Dr. Walker, you collect a tremendous amount of satellite data, imagery, and we have a question that actually speaks to some of the interests that I have, which is how do you manage all of that data in your research? Are you working, are there librarians that you work with who are specifically trained for this? Or do you have archivists? What are some of the requirements that go into preserving this data that you're collecting? And how are your students involved with those kinds of activities?
Well, one answer to that question is that one thing that we do is to create images on a daily basis and archive them on our website so that we and everybody else can look at the images, and we provide animations of the images so we don't like squirrel them away in a computer tape or a hard drive and never look at them. Right now, we're actually taking advantage, I'm trying to think what it's called, LSU's new system that allows us to archive all of our GOES data, which is a tremendous amount of information. The name escapes me, but apparently it's housed by Microsoft, and apparently it has unlimited storage capacities. So that's a good question, because the storage of data has changed over time. The media that you store on has changed over time. And sometimes we end up with an archive that we can't read from, the 90s. So it's a moving target, What we do today isn't what we did, 10 years ago. And the students are involved for sure in all aspects of the operation. Rick Haig would probably be a better person to ask about this, because I don't get involved as much with archiving the data, but I can see that it is a big thing. Nowadays, the federal government has copies of all this, and some of our data we actually get directly from the NOAA cloud. So we don't actually receive all of our data on antenna anymore. So, we don't actually have to archive all the raw data because somebody else has it available. But in the early days, NOAA used to come to our lab because we had more data than they'd had in their archive. So things change over time.
So, I'll put this out to Jill and Barry. Both of you also deal with a tremendous amount of data. Are there specific things that you do to try to handle that in terms of storage and archiving, and then preparing the data so that you can use it in the future, or have it available for longitudinally for when we start to look at things on a much grander scale?
Yeah, well, as state climatologist, I work very closely with the Southern Regional Climate Center. We archive data from all over the country. Um, and a lot of this, this is ingested, through the computers and stored. And we have the ability to do that. And more specifically to my research, we've been archiving the surge data and scraping data from wherever we can possibly find it. Storing it's not a big problem because there aren't that many surge events. It's not that much data really, but managing it and querying it is where the tricky parts come in. And we work very closely with the Southern Regional Climate Center, with the IT folks, David Satyaraj, who actually left LSU to go to a private consulting firm out in California. He's done some tremendous work for us to take our surge data that we've collected and built this database, and then he built a web interface where you can query the data and do searches for an individual storm and get all of our surge data for that storm, or you can click on a location and get the history of surges within a certain radius that you can actually prescribe, whether it's a 15-mile radius around a location or a 50-mile radius, and you could pull in all the highest surges for that area and build a surge history for a region. And so that's available. If anybody would like to play around with that, email me. We've been having some computing issues with it lately, but we're going to be beta testing that very soon. And we can certainly give people, if there are any researchers out there in particular, we can give some access to that and let them query the database.
Jill, anything?
I'll not too much. All I'll add is every year the National Hurricane Center in the summertime usually comes out with the previous year's updates to whatever data exists for every 6 hours. So usually what I do is a type of interpolation procedure that's based in statistics that it gives us hourly data both for intensity as well as position. So if anybody ever wants something like that, I certainly have it available, but none of it really takes much storage, and so much of it is publicly available. So it's stored on other people's hard drives, and then I take it and then drop it onto one of the LSU servers.
Okay. So I'm not sure who would best answer this question, so I'll just throw it up for any of you. How much danger is there in Lake Charles for toxin contamination as a result of the wind? And there was a big fire actually at a chlorine plant. What are the kind of pollution ramifications of Hurricane Laura in the Lake Charles region?
Wow.
Yeah, that's a big one.
That's a little out of our wheelhouse.
I would imagine, but
of course there are numerous petrochemical plants around there, obviously, and who knows what sort of toxins and chemicals people could be exposed to if there were leaks or whatever, if something else was compromised. Having said all that, I will mention that there's obviously no electricity in Lake Charles right now, and there's no water in Lake Charles. And apparently the water supply isn't supposed to be repaired. Probably, I've heard a rumor that it may take until October. And that can't be healthy for that environment. If people are trying to rebuild their houses, and you can't even get water. And you can't flush a toilet. There's going to be some serious problems, and I sure hope they get that fixed sooner rather than later. Otherwise, that's going to really affect the repopulation of the city, much like the problem that New Orleans had post-Katrina, where people go away and you can't come back for 6 or 8 weeks, and then your roots start sinking in pretty deep wherever you are, and it makes it that much harder to ever get back.
So another question comes from our dear friend Hampton Peel. Can someone speak to the issue of waves on top of hurricane storm surge? It's a threat that people are often not prepared for.
Well, obviously, yes, there are waves on top of surge. When we talk about surge, we talk about a still water level. And but in reality, we know that there are waves on top of that are reaching even higher heights than what the actual surge is. And I did a little bit of consulting work way back when with Greg Stone, and waves became part of the issue that we were looking at. And this is a formula that I'm taking from Greg, so I'm pinning this on Greg. But the waves can grow up to 75% of the water depth. So if you're approaching land and you have 10 feet of water, you can have 7.5 feet of waves on top of that.
So a question that that I find interesting and speaks to me because I'm a native Californian. When I was growing up, we heard a lot about El Nino, La Nina as currents that flowed through the equatorial Pacific regions, and that there was always some kind of connection between that and other weather events in other parts of the world. We know that those currents can actually affect the weather on the California coast, including the lightning storms that they've had of late. Is there any correlation between what's been happening in the Pacific with the status of El Nino and La Nina versus what's been happening in the Gulf of late? Or are those systems just too far apart?
I think the Pacific El Nino Southern Oscillation certainly impacts things that happen in the Gulf. We know that when there's an active La Nina happening in the Pacific Ocean, the Gulf of Mexico tends to be heightened as far as how many storms are forming and then how many are able to make landfall on the Gulf Coast or on the eastern seaboard. And then the opposite is true when there's an El Nino in the Pacific Ocean. It means that the Pacific is warmer than usual. They tend to get more typhoons and we tend to get less systems. I think that the firestorms of Northern California, as well as the storms that were happening at the same time at the Gulf of Mexico, they're certainly, I think, separate events, both related to extreme behavior of the atmosphere. There was a lot of moisture available in the tropical Pacific this year associated with the warm sea surface temperatures that they have. And I think a lot of that pushed north into the parts of California that then led to this, this rapid convective event that occurred as it passed over the cold ocean currents. And then you get this rapid change in temperature and some impressive lightning strikes. Which can then, of course, lead to the terrifying forest fires that they've had there. So certainly the active state of the Pacific impacts all of the weather that we see. It doesn't necessarily have to be considered too far away, but I don't think they were related to one another while they were actively happening. And for the record, that question may have come from my mother. I just have to say that. She's in Northern California and is very curious, so it's possible.
I see.
And what this all boils down to, by the way, we get twice as many hurricanes in the Atlantic Basin during La Ninas than we do during El Ninos. It's twice as many. And the simple answer is during La Ninas, it creates a very favorable upper air environment for the storms to vent, whereby during El Ninos, over the breeding grounds in the Atlantic Ocean, even though the El Nino is emanating from the Pacific, but it creates hostile upper air. It creates a lot of wind shear in those environments, and that prevents a lot of storms from forming, and the ones that do form, it helps keep them weaker.
So can any of you speak to kind of what you see into the future as to the ability of the work that you do to point to better information about how hurricanes form, when they're likely to form? How do you see the current technologies evolve to help you be better at what you do, to provide better information for the purpose of public safety?
Anybody?
Nan, do you want to work on that one?
Well, yeah, I have something I could say about that. I would say that right now we have a lot more data, more accurate data, more, we're not very, the federal government in terms of the National Hurricane Center, et cetera, is not keeping up with the data we have. So we have all this satellite data, but it's not being incorporated into the models. And I'm not trying to point fingers, but it's, that's an area that would help with intensity forecasting a lot, is to improve the models that they use. And it's a challenge, because the data is coming in every minute. And so, it seems like they need some kind of extra staff that's just in charge of getting the satellite data into the models or whatever. There's also a lot of other data being collected. So I wanted to talk about that. So in the Gulf, there's glider data. There's a lot of autonomous measurements being made, which is being used for, well, ideally it's being used for hurricane forecasters. Again, it's probably a matter of coming up with the method of using it in a timely fashion. But yeah, the gliders can be sent wherever you want them. They're a little slow, but I think they were out in the Gulf on the track of Laura. I haven't looked into that a lot lately, but I should mention that there's a program called the Gulf of Mexico Coastal Observing System. GCOOS is the acronym, and they have a very nice website where you can go and you can visualize glider data and different satellite data, and also current meter data that's being collected. Just recently, some current meter data is started to be collected. It's called HF radar. It's surface currents that they're in an array off of the Mississippi Delta. So anyway, GCOOS is a very interesting, it's like a data storage facility for oceanographic data. Another group that's very up on this is the AOML, the Atlantic Ocean Meteorological Lab, I think it is, Atlantic, yeah. They're also within NOAA. And they have I'm trying to think of that. It's an ocean viewer webpage. So, in fact, I just discovered it not too long ago, and that's a good place for anyone interested in hurricanes and data being collected in the ocean, in particular, to go and see how that's relating to intensity of hurricanes. But yeah, it's a challenge. I had an email with a fellow, Nick Shea at University of Miami, and he is an oceanographer, and he makes measurements from the hurricane hunters. He drops instrumentation into the ocean. They go down about 1,000 meters, and so they're measuring the ocean heat content. And to my knowledge, those are not being used either in the forecast. So there's a lot of data being collected that's not being used. And he told me that the National Hurricane Center is still using their statistical model for intensity changes. So they're not actually using a numerical circulation model for the hurricane intensity. So there's a lot of room for improvement there. I feel like right now with the new GOES sensor, we have more data than we know what to do with, But
those are problems we should all have, right?
Yeah, right.
Yeah, I think that's a bit. I mean, we're overwhelmed with data now.
Yeah, I know. I know.
If you look at the history of forecasting, though, I mean, if you think about the Galveston hurricane of 1900, those folks on that beach didn't even know a hurricane was coming until the island was enveloped. So the technology and in forecasting has really come a long way over the 120 years. But I do find it kind of interesting. I mean, I guess we discovered fronts and started using that terminology in the early 1920s, and then we have the aircraft that could fly into the hurricanes in the 40s and satellites in the late 60s. Chaos theory is probably one of the last great discoveries in the early 60s. I would argue since then, though, I mean, we're inching the forecasting along, but there really haven't been any tremendous breakthroughs in our understanding of how the atmosphere works, much less hurricanes. And but again, the computing power, the computers are getting faster. We're processing more and bigger data, and it's enabling us to do bigger and better things. But the fundamentals, though, we're really not that much further along now than I would say we were 30 years ago.
Right. I think the prediction of track has improved a lot because the numerical circulation models are a lot better. And that's probably a function of, mainly the computer speed and that kind of thing. I'm not a modeler, so I shouldn't be venturing into that arena very far.
That's fine. Well, it's time for us to bring this to a close. Thank you for such an engaging presentation and conversation, both to you and to our audience for the great questions. I'm happy to announce that tonight's lucky winner of the WRKF cooler is Gretchen Stein. WRKF will mail you the information and get that to you as soon as they can. We also hope to see you on September 29th for our next Science Cafe. It'll be a talk about music with some of my colleagues from the School of Music. I really appreciate everyone coming here. This concludes the live closed captioning event. Thank you all very much for attending. Good night.